精彩的地方都没录到。好，没办法，待会再讲。OK，sorry。Okay, so our purpose is here. So back to here. So this 2D. And we try to find a discrimination line. And the discrimination line is controlled by the W, the parameters, rotation, translation. And they will project to this the normal direction of discrimination line. So there were two Gaussian distribution here. This Gaussian, this is the other Gaussian 2D in 2D. And we project here, there were one Gaussian here, a second Gaussian here. Okay. And we try to, the purpose, we hope I can maximize this one. And this is an example. But this example is not so good. This meaning if you project to here, right? So this is first the Gaussian distribution, the mean value. This is the second one, the mean. So our purpose is try to that both average value, mean value be away, and that is standard deviation. This is better. That the standard deviation is smaller. This standard deviation is too far, too wider. It's not good. Too wide doesn't mean never. The overlap area is big. Okay, so back to here. So that's our equation, our constraint. So what's the M? They have a header here. Tell me the header. Header, this one meaning projection in 1D, in low dimension. So here, so suppose in 2D is X. So we assume it's a Gaussian distribution. So we find the mean value of first Gaussian distribution. Suppose N1. This is distribution X1 is this one. Suppose X is or X, and then we do the X. X is 2D, okay? And so M will be average value or mean value of two distribution, okay? And when they project to the normal direction, so we have projection mean. So what's the projection mean? The average is easy, just sum all together, right? Sample one, summation all the position of sample one and divided by total number will be the average position for cluster one and for cluster two. And this one is, we try to find what's the projection average value or mean value. So it's the original for each X will based on the W projection, the inner product and project. So what's the X? So this is this one. Suppose each point here. So there will be any X and they will project to the W here. Or this is the other W. We don't know which W is good. This W will control one line. 就是这个 W 有三条线，表示这里有三条线。那 W 就 control the rotation translation. Okay, so any in the 2D, any X they will project to the W. So this X vector project to the W vector. The inner projection is the inner product. Inner product is cosine theta. Okay. So that's here. They would write. They define here. Defines any Y. This is 2D, and this is the projection value in this one in the W direction. 投影 W 是它投影在1D 上这样子。So any X project to the W equal to Y. 任何2D project 经过 project 到这条 W 线上的内积嘛，就等于 Y 的量。So this is inner product. This is meaning inner product. Okay. 那我上次讲的那个轴，任何轴是一个 any axis should be unit vector，所以是 unit vector，是单位向量的啊。那个轴要单位向量，这是在 constraint。回到这里 ，so any point in 2D we project to the normal direction, it will be projection y is one, the component of y. So this is 1D, is 2D. Okay. And continue. So because W is constant term, so we can move the constant term outside from here to here, move constant term to the outside. So you will find out this term equal to this term. So this term is the average, the mean value in 2D. So that's meaning in the 1D, the mean value of 1D equal to the mean value of 2D project on the W, the normal direction. 就是你的1D 的那个group 的平均高均的中心点平均值等于2D 高均 distribution 或高纬度高均 distribution 投影到低纬度的轴上，所以你的命值是不变的，只是直接投影就好了。意思是说 ，the meaning is that you don't need to calculate of it in the original dimension. You just calculate the average value based on the average value or mean value. You just directly project to the W, and you got a low dimension mean value here to tell you this thing. So here we can continue to change here. So final one is this one. Here. This page. Okay. So on page 5, you will find out. Okay. This is any here. Okay. What I try to say here. Based on this equation, right? Average value. And this is a standard deviation. You want to higher average value, lower standard deviation. Okay. So we already have a mean value here. This is a previous page 3. So mean value, right? The mean value equal to original mean value directly project to the W. So this here. Any mean value in high dimension project to the W equal to low dimension mean value. It's this one. And this is standard deviation in the low dimension, the standard deviation in low dimension. So that's meaning in low dimension, any sample in low dimension subtract with the low dimension mean value. It should divide the total number. So that was standard deviation in the low dimension. So that's meaning this low dimension. So low dimension equal to this original high dimension, right? Standard deviation, original high dimension sample, high dimension mean. This high dimension, and this is low dimension. But actually, you don't care about this one. You just care about this one. So this one equal to from here, this one. And the purpose is try to find W. Our purpose is try to find W because we don't know W. But we don't want to maximize this one. We want to maximize this equation. Maximize this one is meaning in the low dimension, the center between two Gaussian distribution will be bigger. So larger this one. Also, we try to, for each standard deviation should be lower. So we try to maximize this one in order to find W. W is we try to find unknown. So final is this one on page 5. So we'll find in the this what we check this term first. So this is the denominator term, 是分子的 term， 分子这个 term， this term equal to this term, denominator term of Jacobian. Right, so we try to, this term will equal to, what's the W? So this term, right, the distance between two mean value in low dimension, the distance between two mean value in low dimension, so equal to the distance in high dimension mean project to the W. But it's square, so it's square, two terms. And we define this mean value because we can capture the mean value here equal to this one. So the purpose is try to find W. Okay, I say again. This is our constraint equation. Our equation. Equation is that when we in high dimension project to a low dimension, based on the W. 从高纬度投影到低纬度是经过 W. Now, in low dimension, we hope the two Gaussian distribution. So we hope the Gaussian distribution of the average, the mean value be apart. 这两个越大越好. But the standard deviation smaller is better. So we continue from this one. We try to find W. So from here, we try to find W. So this original. So the original in the low dimension mean value of two Gaussians equal to original mean value in high dimension project to the W. And this square, so equal to this one. So we define this called between. B is between two mean value of Gaussian distribution. So this between. And this is the within, this standard deviation. So standard deviation here. In a high dimension, any sample, right, subtract with the mean value. So this is the standard deviation. And then because we have a standard deviation 1 and standard deviation 2, so we are this 1 plus 2, so will become this one. But that is high dimension, so we can project to low dimension. So with W, the same as this one. 这是高纬度嘛，那我们要投影到低纬度有个 W 存在，所以这是 standard deviation. So original equation from here will become this one. And based on, we call this is between this within. That's important. And we try to find W. So we try to maximize this one. And we try to maximize or minimize this equation. We find W, so we derive the derivative with the W. 我们要求 W 就跟 W 做微分嘛，很简单。微分的就是这个 equation。那个微分方程式我把它写在这里。这个微分有分子分母的 term， 微分方程式我写在这里。那这个最后解出来，你会发啊，尤其是这个因就解出来又 find become here, and this term equal to Jacobian. Jacobian is a constant, 是一个常数项。We want to maximize this one, so this become a constant term. We assume this constant term to be a lambda. This constant term to be lambda. So we derive this one to the W, become this term. And this term is a constant term, so we use one constant term here. And then this is a SW, so we move SW to here. So this is your final term. And you will find this final term the same as eigenvector. This eigenvector, this eigenvalue. Sorry, this eigenvalue, this eigenvector. So I said PCA singular value decomposition, sometimes we apply SVD to optimization. So so we find this constant term, this one is an eigenvalue, this eigenvector equal to one matrix times eigenvalue, eigenvector. So we move eigenvector to here. So that's meaning based on the SW minus this denominator and denominator, this one, we do singular value decomposition. We can find W and eigenvalue. Because we try to find maximum value of this one. So that's meaning maximum value of eigenvalue corresponding to the eigenvector. That's your answer, W. 就是说你这样经过这个微分离以后，你会这个式子，那这个式子刚好这个式就是这个式子，那这个式子你把它当成，因为这是你要 maximize 这个term嘛，那这是一个常数项，就把常数项当成是 lambda。哎，你发现我把 SW 再把它移过来，这 SW 移过来，那你就发现这个 term 刚好是 eigenvalue eigenvector 乘上这个 A matrix 一个 matrix A， 那乘上 eigenvector， 那这个 eigenvector 你把它移过来，意思就是说这个解就刚好是你 SW 减一跟 SW， 这是分母啊，分母跟分子。经过 SVD 完以后，就会找出 eigenvector 跟 eigenvalue， 所以它是用 SVD 的方式来解这个 equation。那 SW 是什么 ？SW 就是刚刚讲的这个，就 within 是什么 ？within 就是我本身这个 class，within 是 meaning my class，your class，so that's standard deviation。What's the between? Between is our average value. So LDA is used for what? Used for discrimination of two or multiple classes. And the purpose is you try to find an axis, projection axis. Okay, that's W. This axis will allow each average value of a Gaussian distribution to be apart. However, also try to find for each cluster be closer together. 就每个群组要越集中越好，然后我跟你之间要越分开越好，这样子。Okay, so you can find W. So W is what? W actually is this line, but this is normal direction of the discrimination line. 记得 W 不是那条你要求的线哦，不是哦。W 是你求的那条线的 normal direction. 所以你的 your line will be here somewhere. Now W is the projection line. So each point can project on here. And this projection line can be separate, both cluster. So your discrimination line is here. 你的 discrimination line 可能是在这个某个地方，是这一条线，垂直的线，这是它 normal direction。这个不要搞混了。You try to find the separation line. Actually, you try to find the projection line. Projection line W is the normal direction of your separation line. 这样子 because your W is control the rotation. Also, if you have a constant translation, 所以你要找是找 W 这样子，看一下，所以回到这一边。So your purpose is try to find this W because this W. So your purpose is try to find this W. And any point project on this W. So W will be you try to the W any Gaussian you project to this W, and you will try to the mean value of Gaussian distribution will be apart, and for standard deviation will be closer. Okay, now 画一下。 So two distribution, right? So if your W is like this way, and you project to, let's do this one, let's do this one. So if so if you project to this line, you will find this one will become here, and this one will become here. So your two Gaussian will be like this one. So overlap will be big overlap. I mean, if you W this one, and you project to this one, this project to here, so this standard deviation is too wide, and this one is this one. So your two Gaussian will overlap a lot. So if so, the better line will be here, right? This is better. This will be better if you project to here, and the average will be here. And both distribution, Gaussian distribution, will be separate. 这个高兴会比较开这样子。So the purpose is try to find the best W here. And W is the normal direction of discrimination line. 这个不要搞混了这样子。OK， 那我最后总结哈，说 So what's the PCA for? PCA is actually when we do the research, when we do the discrimination, we will combine PCA and LDA. PCA is that allow you to from higher dimension project to the lower dimension. If you directly use LDA without PCA, the dimension is too high. That's not good. Okay, so PCA allow you to from very high dimension project to the lower dimension. And after PCA, and you do the LDA, because LDA will be that the same samples be closer together. Different samples will be separate away. PCA is only for each sample is individual. PCA 是把每个点都，不管你同个人，假如我同个人拍5张照片，每个人都拍5张照片。PCA, so any person, suppose you take four photos. Suppose have 3 person, each one is five photos. So total have a 3 by 5, have a 15 samples. PCA is just try to let the 15 samples to be apart as possible. PCA 不管它没有 within 的观念 ，PCA 只是让这15个点越分开越好。PCA is only consider the between relationship without within. So that's mean those 15 samples, 3%, each person is 5 points, 5 samples. I mean, take 5 different angles, right? So 15 samples you put on PCA. PCA will let the 15 samples be apart as possible. But PCA allow you to project from the sample from high dimension to low dimension. That's the major purpose. And then LDA, the purpose is try to let the 5 photos, the same person, different pose will be closer together. Different person will be away as possible. 所以 LDA 是让有群越相同的人的，像我5个不同角度之后，它会让这5个角度同个人嘛越集中越好，不同的人会越分开越好。所以 LDA 是有这个 within 跟 between 的观念 ，PCA 没有那个 within 的观念，只有 between， 就让它分散越好。但是 PCA 可以把你纬度降低非常多 ，LDA 没有什么降低纬度的功能，这两个不一样。So when we do the discrimination, we will use PCA plus LDA. You cannot only use PCA, you also cannot only use LDA. you should use both. Okay. And next class, we'll talk about SVM. SVM is totally different from, if you use SVM, you don't need to use the PCA and LDA. There's difference. So PCA plus LDA is trying to project the sample to the lower dimension. SVM is trying to reproject to the very high dimension in order to do the discrimination. 这两个不一样哦，一个是往低纬度走，一个是往高纬度走，这样子。Okay, so that's it for the first hour, and then we take a break and we talk about second hour. We'll talk about the homework, the solution of the homework, and talk about SVM.